Hello, my name is Barnard,
I'm Dylan Smith.
and we are the engineers on RD research, and we made the Ridley processor. Today on our agenda, we're going to go over the team, how it was made, the Ridley processor itself with a slight overview, our enhancement, the MIPS Mini, future considerations for our project, and any final questions that you may have at the end. RD Research and Design was formed to create an enhanced form 32-bit MIPS ISA, and it was created by the two engineers, myself and Dylan. The Ridley, it is our processor. It is a combination of both of our names. That's how I came up with the idea of it. And it's also the name of one of the main antagonists in the video game we both enjoy. And it is an enhanced MIPS processor capable of integer broadsiding.
And the Ridley processor is a 32-bit MIPS architecture. It's capable of running any MIPS program. As such, it's also a RISC architecture processor. The only memory accesses available are loads and stores. It uses a 32-bit memory address, and it has 1K by 32 byte addressable memory. There are 55 instructions in the Ridley processor. That's 18 over the required baseline, and there are 3 data types and 3 addressing modes. And this is the register set and data types that are available. This chart shows the conventional register uses in most MIPS programming. The 32 by 32 register file is used for any internal register operations, and then we're able to use a 32-bit unsigned or signed integer and an 8-bit signed integer as well.
The 3 addressing modes that we will be able to use are register direct, which is most commonly used to perform arithmetic operations between 2 registers and saving the result in another register. Register indirect, which is used for load, store, and jump operations using a sign extension. And the immediate value uses the lower 16 bits of the 32-bit instruction to calculate jumps and jumps address.
And then we have our available instruction types here. The R-type instruction, the I-type, and the J-type are the standard MIPS instructions. The R-type is used for any register direct operations. The I-type is used for any 16-bit immediate operations or any register indirect operations. And the J-type is used solely for unconditional jumps. At the bottom you'll see the E-type, and that's used directly for our MIPS Mini arithmetic unit, and the word type for that breaks down to use the 1F opcode similar to the R-type instructions. There's an RS and an RT source field and the RD destination field. Because the MIPS Mini only operates on an 8-bit signed integer, the shift amount is reduced down to 3 bits. And that allows us to create the lane control, which will be talked about in the detailed overview of the MIPS Mini. And there are 4 bits of function select available.
This is our top level diagram. It consists of the CPU and data and input-output memories. The CPU is made up of the MCU, the instruction unit, and the integer data path, with flags leaving from the integer data path to go back to the MCU, and any data and address to come out to go to either data memory or input-output memory. And for write back as well, this is our instruction unit. It consists of a MUX connected to a program counter, which then outputs into our byte addressable memory. We cannot actually write to this memory, but so we can only assert the chip select and the read, and that feeds into our instruction register and sign extension that lead out into our ALU.
Just a little question back on that guy. Why can't you write to it?
We deasserted write because our design in the processor does not allow any rewriting of the instruction memory. As a result, we grounded the write control to prevent any erroneous writing.
So you could, though,
You could
if
write
you
to
wanted
it,
to
but
have that kind of
in hardware
enhancement.
it's currently grounded.
Okay.
And then we have our data and instruction memory, or data and I/O memory. Both of these are byte addressable memories. They are identical in design. It is a chip select, a write, and a read. If the chip select is not asserted, both memories will output high impedance. If the chip select and the write is asserted, the memory will be written to. If the chip select and read is asserted, the data on the address line will be outputted.
This is our integer data path. Kind of big, but it begins with our 32 by 32 register file that have the MIPS 32 registers in it that we usually write to. There is an RT and RS register, which are used basically to hold the values before we pump them into either the MIPS Mini module or the 32-bit ALU. The 32-bit ALU will output into either the low or high or ALU registers. And high and low are normally used when we're performing multiplies or divides. And if using a multiply, the upper 32 bits of the 64-bit product will be put into high, the lower will be put into low, and when doing a divide, the quotient will be put into low and the remainder will be stored into high. And they will stay there until we actually perform a move from high or move from low, and then that will be pumped into the 8-bit mux that we have. That will then go back to the address that we used either for address or write back into the register file. The MIPS Mini has something similar because the 32-bit ALU has T and S. That one also has a T and S, but this one features a lane control. They also output into certain registers such as a mini low and mini high. So when we perform a multiplication or a division in the same manner, it stores them in the mini high, mini low, and then the mini ALU is also where it is stored for any other operation.
And the MIPS Mini is our major enhancement to the MIPS baseline processor. MIPS Mini is short for MIPS Multiple Integer Simultaneous Instruction Unit, and what it does is it is an SIMD vector type unit. It takes in 4 bytes, operates on them individually by byte, and outputs 4 separate bytes as well. This is a sample of how the MIPS Mini is actually developed. As you can see, it's a very simple unit. There is 4 of these in the actual module. It's 4 copies of the same 8-bit ALU. The 8-bit ALU itself is scaled down from the 32-bit ALU. And each ALU 8 looks just like this. It is a multiply unit, a division unit, a full arithmetic logic unit, and then a barrel shifter. The barrel shifter does have a few minor bugs. It's currently in development and will be updated shortly. And what is not shown in here due to the space of the slide is the actual logic for controlling the design. In the ALU 8 module, there is a lane control enable. What the lane control does is it's a single bit input that when asserted, the ALU will do the operation as planned. When it is deasserted, the ALU will output, that single 8-bit ALU will output 8 bits of 0, and it will not update the flags. The flags will be set to an X or a don't care. This is the structural design of the MIPS Mini. As you can see, it's the 4 parallel 8-bit ALUs. The lane control comes in right here as a 4-bit signal and is tapped off to be 4 individual 1-bit signals to each ALU. The 3-bit shift amount is passed in parallel to each ALU, and the function select is as well passed parallel to each ALU. As you can see how the inputs are actually handled, the RS and RT fields of the input to the MIPS Mini are actually pulled in and tapped off to be 4 8-bit values for the 4 ALUs.
So again, the lane control, the purpose of the lane control?
The purpose of the lane control is to allow for the 4 parallel bytes of the MIPS Mini to be used instead by programmer. It gives the programmer the ability to either do 4 bytes or any combination of the 4 bytes that are sent in. The lane control is a 4-bit value so that there's full control for each one. If you wanted to, when testing the when programming this processor, you can actually set the lane control, for example, to be an 8, and that would be 3 of the ALUs on and 1 ALU off. The ALU that was deasserted would output zeros on both lines, the rest of them would compute as normal.
Okay. So it's just output zeros if you want to?
Yes.
Kind of like, don't use that particular slice?
Yeah.
Okay.
And this is how the data is actually packaged in the MIPS Mini. This is the same for the mini ALU register and the high and low registers. The first byte is stored into the upper 8 bits, second byte to the middle 8-bit, or the 23rd to 16 bits, the second lowest byte to the second lowest byte, and the lowest 8 bits, the lowest byte. Again, here's the instruction format, and as was noted, the lane control. And due to the way this instruction is formatted, there are only 16 operations available for the MIPS Mini run. And here's our table of the actual full 16 operations used in the MIPS Mini. Since everything is designed to be primarily signed, the only unsigned operation is the set less than unsigned for a simple compare. Everything else is a signed operation. And this is an example of the MIPS Mini computation versus the MIPS ALU computation. It's a small slice, but it shows a data set we use to test it. And as you can see with this data set, both an add in the MIPS Mini or an add in the MIPS ALU will produce the same exact result, but a multiply, which would produce a 16-bit output,
Right.
will show that each multiplication is its own separate value, and any carry or any overflow can, as a result of the operation, does not move into the next byte, versus what would be shown here in the standard MIPS ALU, where any carry for the larger than, in this case, 64-bit output actually flows over to the next 8 bits of operation.
These are enhanced instructions that we added for this Mini. We have the Mini move from low and Mini move from high. Those are just used to access the Mini high and Mini low registers when we perform a multiplication or divide. So the codes are 28 and 29. For input and output, we enable access to the I/O memory space, and we just simply started that with 1C and 1D, and then return from interrupt allows the processor to return from an interrupt by putting the flags on the stack. And these are the future plans that we had, one of which would be to actually pipeline this. We can use it for pipelining. It is pretty close to being used for pipelining. The only problem is we didn't have a forwarding unit, and we didn't put set registers for different stages of the pipeline. However, we can definitely look forward to doing this because the forwarding unit will help us deal with any of the data hazards that may occur from wanting to do an instruction before it's actually ready.
And then as well, another option we want to look forward to is actually to take the MIPS Mini and make it its own coprocessor. Make it a native 8-bit coprocessor built into the current Ridley processor. And all that would be needed for this would be to create the register file and a separate control unit for the MIPS Mini.
We wanted to implement a division by zero flag just because we wanted to check for this error because we didn't want it to actually break our system, just in case someone decided to try dividing by zero. And it's actually pretty simple to implement. The only problem is we just didn't really have enough time to do it. However, the idea is really not how to.
And of course the last step would be to restructure it for synthesis. Currently, all modules except for the control unit are actually synthesizable. The control unit does use #1 statements to progress the simulation forward. All other structural modules, though, are fully synthesizable.
Yeah, if you pull out those #1s, should be synthesizable.
Any final questions?
I guess not. Good job, you guys.